Good. So, good morning, everyone, and welcome to the fourth and final lecture of my introduction to scattering amplitudes and Feynman integrals. So, last time we entered the realm of loops in quantum field theory beyond tree level, beyond the classical contribution. And since things are become quite complicated in this setting, much more complicated than at tree level, we focus not on scattering amplitudes, but on their building blocks, Feynman integrals. One derives from the Feynman rules, from the path integral or the Lagrangian. And in particular, I'm recalling that yesterday we gave the general form of Feynman integral and also somehow transformed it in this mixed representation where you have an integration over the internal momenta, but you also have additional variables, the so-called Feynman variables or Feynman parameters that allow you to pick everything in a single denominator. And I made a mistake last time, I typoed, there's an n factor over there. So Q's are the propagators, sorry, Q minus M are the Q square minus M square are the propagators of the Feynman graph that are normally you have a product thereof in a Feynman integral. And with the Feynman trick, you write them all in one denominator and sound by these variables, Feynman variables. And we asked ourselves, what are the singularities of Feynman integrals, which are more easily derived, were derived by Landau back in '59 from this representation Feynman integrals, and they boil down to these two sets of equations where we discussed essentially generalizing the simple example we started with of a one variable integral and a single integral. We saw that they generalize these equations, that in order to have a real singularity, you need to have that, the denominator vanishes necessarily, but also that the contour is trapped between colliding poles of the integrand so that it cannot escape. And so this then translates to these equations. There were some questions raised, so let's start with this. The first question that was raised was that, these two equations certainly imply that the denominator vanishes. So they are consistent with this equation, but it could be that the denominator vanishes even when not these individually are equal, not every term in the sum is individually equal to 0. So are we missing something? And the answer to this, I believe, and I can be challenged, is that this is an integral not in just the k's, the momenta, but also the alpha. So we need to differentiate not with respect to just k. So this is a differentiation with respect to k, the loop momentum for every loop. We also need to differentiate with respect to the alphas, the denominator. And therefore, if you differentiate with respect to the alpha, that means that, every individual propagator must vanish. So that's this part of the equation. Or you need to be at an endpoint, and this is where alpha equals to 0. So this is therefore this equation. So maybe it was not presented as clearly last time. Maybe we said that this is the first equation, this is the second equation. That's not quite true. These equations combined are the analogs of these equations over here in the single variable case. So that's, I believe, the right interpretation and the right answer to the question that was raised.
Not to mathematical satisfaction because we have to differentiate. So the G is the whole thing to the power n.
Now you're asking about the power n. Now that's a different question. Okay, that's a different question. Yes, but It's true, but actually you need to have a true singularity. Uh, you so if you have, let's say, two poles approaching the same point from the same side, you still don't get a singularity. They need to approach from opposite sides. So this power n, if yes, um, yes, but your point was that these are higher order poles, then you you'll be pinching automatically. I beg to differ. I think that making poles higher, so you see this kind of condition, this differential derivative of the integrand irrespective of the power, means that the roots coincide on the contour, but they're not like they are not identical to each other. So it's not a matter of multiplicity of poles. You should have two different poles that really meet on the contour.
Yes, but in the previous example, these conditions, yeah, all could mean in whatever way they like. From your condition, it's not clear.
No, no, I agree. And this is why these are necessary conditions. But this, I think, answers the question of the power n. The power n is irrelevant for these equations. Yes, exactly, exactly, exactly. So these were some of yes the very interesting questions that were raised, and also we did think step by step just to get a hand of these equations. For the example of the bubble integral, okay, p minus p, and so on. And we saw that, okay, these equations, one can solve them relatively simply in this example, but there is one particular solution that is very hard to detect because it is a limiting solution. You have to um, uh, uh, basically take a limit of some variable, in this case, the third, let's say, component of the momentum to infinity, and these equations hold in this limiting manner. In fact, some of the alphas go to infinity also as you take this component of the momentum, the loop momentum to infinity. So while complete, they cannot be systematically solved very easily. One has to, and that's why in many cases there were singularities that were solved. That's one of the reasons why Landau analysis is a very, very hot topic of uh, research in theoretical particle physics nowadays. And there are some alternative approaches which I will just very briefly mention, just to whet your appetite. And they come also with associated software. So one can try things for themselves and try to compute singularities. One comes to the work on Francis Brown in 2009, and also Eric Panzer later in 2014, and has culminated the program Hyperint for the Maple, yes, software, scientific software, which does integrations, direct integrations, and also computes Landau singularities. But so this program, in order to be fast enough and also certainly not miss singularities, it also computes certain spurious singularities. So also finds spurious singularities. It provides with a list which is bigger than the actual list of singularities of integrals in certain cases. Then more recently we had also work by Vola, Misera, and Telen. So this is last year. This is the so-called principal Landau determinants approach, which is also very fast, but it again misses singularity. So, and they have, okay, the program PLD, I forgot to say, PLD, which allows you to try your luck with some integrals, but it has been certainly established that also misses certain singularities, much the same vein that if one is not careful, one does not even detect this, this so-called type 2 Landau singularity. And then in work I did with a mathematician, Martin Helmer, and also my student, then student, now current postdoc, Felix Telander. We also used the technology of Whitney stratifications, so from algebraic geometry. And the package, the software package that also can be used is called Whitney stratification. This was developed particularly by our mathematician collaborator, Martin Helmer. This one, we showed that it gives the complete and non-redundant set. So, set of singularities as a proof of principle, but nevertheless, okay, admittedly, it's slower, meaning also that in some so complicated cases, it never ends, it never finishes. But we find it quite promising research direction because we have now a definition, in a sense, a reformulation of the definition of Landau singularities in a way that can be practically put on the computer, and it's a matter of increasing its efficiency. So that's some of the things that I had planned for last time, but since I didn't get there, I thought I would just also mention them briefly today before we move to the main meat, the main topic of today's lecture. Any questions about Landau singularity? Physical, in the sense of whether they appear on the physical sheet? No, no. We care them because if we think of well, I will answer this today actually, but the general answer is that Feynman integrals are multi-valued functions, and you might start from the physical region and analytically continue, follow some path, some monodromy, and come back and keep doing it. And in some sheet, you will encounter them. Why this is important, I will talk about today. More questions? Okay, so let's then move on to the new stuff, which will be, okay, I will, in less than 2 hours, I will try to give you a glimpse on how direct Feynman integration works. What is the current state of the art? How do we actually go about it? So I will just write the title in blue and hopefully it will be visible. So it's direct integration. In particular with polylogarithmic functions, with polylogarithmic functions. We also said last time that Feynman integrals by construction also include logarithmic singularities, so it's not a surprise that some kind of generalization of this function plays a role for Feynman integrals. And so let's ask, how are multi-loop integrals computed? So, okay, in the first step that we have learned from our quantum mechanics, quantum field theory course, you have some amplitude, and you write it as a sum, well, in fact, multi-loop amplitudes. Let's start a bit more general. Amplitudes. So a loop Feynman, sorry, amplitude is a sum of L loop Feynman diagrams. We all know that, no surprise. But it's good to recall that these are tensors in Lorentz indices. So the previous definition, the previous form of Feynman integrals I had, everything was a Lorentz scalar. Nevertheless, what naturally comes from the process of applying the Feynman rules is some numerators that might have Lorentz indices. For example, you could have something like d for k to the mu in the numerator. So you could have some numerator, numerator that has an open index or several ones, or combinations of internal and external momenta. So the first step we do is we reduce tensor to scalar integrals. And it's due to the work of Tarasov in 96, 97, that we can always do this. So I will not say how. The idea is that one needs to also enlarge the way we think about Feynman integrals so that their dimension also changes, the loop integration dimension. So this d might change, might increase or decrease by 2, but we can always do it. So this, I will unfortunately not have time to discuss how it's done in practice, and you will have to take my word for it. But hopefully, it's not that much of a leap of faith. Somehow writing out, products and some kind of group theory decomposition, if you want, of the Lorentz group. And then what we do is we eliminate, so we have arrived at scalar integrals, and we eliminate the huge redundancy they have, meaning linear identities. If you have 3 integrals, I1, I2, and I3, it might be that I3 is 2I1 and 3I2. So they are not all independent. So if we try to compute them, we are working more than we should. We are making our life harder, and this can be a huge, huge number. And so the reason for these linear identities, among them, is the translational invariance. Translational invariance of integrals in dimensional regularization. So we already mentioned last time that we make, dimension d to be some integer minus 2 epsilon. This way takes care of infrared and ultraviolet divergences of the integrals. And so if we still continue to use this kind of regularization, and we will, it's important because precisely in other types of regularizations, Pauli-Villars, where you you have some infinite integration, but you cut it off, you put some cutoff, the cutoff breaks translational invariance. So that's why it's a statement that is tied to dimensional regularization. So in this case, the statement is that some integral in one loop integration, say, it's the same thing, but yes, this is no loss of generality, is the same if you shift the scalar, yes, integral with some random momentum q. That's the statement of translational invariant. And then from Taylor expansion, so Taylor expansion in lambda, where lambda is some small parameter, we put it, yes, just to be able to do a Taylor expansion. This means that dk ip d over 2 is 0. It's really a matter of taking the Taylor expansion, and you can give it a try if you are not convinced. Yes, essentially you'd expand the the right hand side, and you cancel the first term, and the second term is this one. You see, if we differentiate the integrand where we multiply it with a random, an arbitrary vector q, this gives 0. And this can be any combination, any combo of internal or external momentum. And so in 4D, you would have a UV cutoff, which would mean that this integral will not go from minus infinity to infinity. It would go up to certain value. And therefore, yes, it's the fact that you have an infinite range that allows you to shift k by some. Gives you that infinite range because you don't touch the range of integration. What you touch is the dimension of the loop integration momentum. I'm sorry, and this should be d. I'm sorry. That's why. You don't change, yes, the range of integration. You just change the dimension of integration, precisely. And these are called, not surprisingly, integration by parts identities. Or IBPs. And the solution of these identities of IBPs, which are linear identities, is called also a basis of integrals in the standard sense that any other integral can be written as a linear combination thereof. And they are also called sometimes master integrals. Maybe deceptively, like deceptive terminology is really just a basis in this linear space. And to find them, so in order to find them, we need to generalize Feynman integrals to have integer propagator powers. So going back to the general form of a Feynman integral that I wrote down on the previous lecture, related also to this other representation I wrote earlier today, is the following. Let me just be very concrete, and we will also go back to our example of the bubble to illustrate everything. So this integral depends on the dimension, and as we said, depends on the external momenta, and it's an integral for all loop momenta up to some normalization. I didn't change the normalization. And you have the propagators, just to be very concrete again. So this is I equals 1 to n, mi square minus qi square minus the causal prescription for the propagators. And now they come with this integer propagator powers. The reason is that doing this kind of differentiation, you can see it with the masses. It will just change this propagator power. So to be able to solve the identities, you need to generalize in this way. And then, okay, once you find the basis, you can perhaps only think about the integrals that have propagator powers 1. But you need to do this generalization to solve the identities. The Q's are, again, sums of internal and external momenta. I don't need to write them down, right? We wrote them down last time in the sense that they are sums, yes, of Q's and P's, linear sums of P's and Q's. And let's come back to our example of the bubble to see those IBPs. So IBP example, again, the one loop bubble. Where we, shall I write it down again? Just for the notation again. So I nu1, nu2, d, and now it depends on p squared, m1 squared, and m2 squared, the Mandelstam invariance related to it. And this has a single integration. Okay. D over 2 has two propagators, so it also has. Okay, I'm dropping also the Feynman causal prescription. Just the two propagate. And now, if you apply this equation here, let's see how big the equation is. Oh, it's not too bad. And what are the options that we have for the momentum Q in this example? What are the momenta that we have in this problem? Yes? Okay, that's one. And what else? Exactly. Only two options. It's simple. There isn't much we can do with just two momenta. So let's try, I will just write down. So this is for you to give. K by K, it's you're differentiating. So this is a summed index. I don't understand what you mean.
And previously, you shift K by number.
Yes.
And then you ask me what you can be K.
It's like rescaling K.
Yeah.
It's also a rescaling. That's also allowed.
Scaling will change masses. Well, let's see.
Yes, let's see how it looks. So for the first case, you get something like d minus 2 nu 1 minus nu 2 I nu 1 nu 2 minus nu 2 I nu 1 minus 1 nu 1 plus 1. Yes, very good. And then you get also minus nu 2 p square minus m1 square minus m2 square times nu 1 nu 2 plus 1. So this is, in case for people in the video, this is the integral with indices nu 1 and then nu 2 plus 1. And then finally, we have minus 2 nu 1 m1 square I nu 1 plus 1 nu 2 equals 0. So if you are inclined, you should give it a try. And I should say that today I am mostly following references. Yes, chapter 3 of the SageX review. So mostly following. I think this is a reference 3, and then Weinzierl's book is a reference 7, but okay. Let me write it. SageX review chapter 3, and also Weinzierl's book. And I say this because you can give it a try, and you can also go, let's say, to review chapter 3 to figure out the details if you if something doesn't click. But the important thing to keep is that evidently integration by parts identities change the indices. That's why you need to generalize them in order to be able to solve the identities. And then similarly, okay, I would not write down the second equation, but it follows in a similar manner. And the end result is that the basis is a three-dimensional basis, which can be chosen to be our standard integral, the bubble that we started with, and also integrals which have 0 propagator power. And this is just like removing an edge from your Feynman graph. So this is the graph that you started with. And these are tadpoles. They are tadpole diagrams, massive tadpole diagrams. So this process, that's another general feature. You see it in example, that's a general feature. It can also delete edges, not maintain them all. And that's why when we do this, we talk about integral families. Integral families or topologies. because this integral family also contains all integrals that where some of the edges have been removed. So, and yes, it's in this example a three-dimensional base, and every other integral in this family can be written as a linear combination. Questions about IDPs? Yes, you don't have P dependence. It's just it just depends on the mass. Absolutely.
So the all integrals must be, I mean, it seems a very useful property in integral invariant in this Albertine constant ship. But when you make Q pay in terms of scaling, that must be just a special plus. What we did was a statement that we just write everything under integral. That will be just total derivative. That's
Yes, that's the whole point. It's a total derivative, no matter what. So, okay, we are at the stage now. We started with writing down all Feynman diagrams. You have to take my word for it that I. Yes, masses can also be zero. And but if your masses are zero, then this number of master integrals changes also. For example, if the masses are zero, this becomes scaleless integrals. And scalar integrals are set to zero in dimensional regularization. So the number of master integrals does depend on whether the masses or the momenta, for that matter, are zero or non-zero, shell or on-shell. Yes. Okay, so we started with a sum of Feynman diagrams that were tensor. Uh, we made them scalar. You have to take my word for it. We then find the basis, remove all the redundancy by finding a basis. In this example, these three integrals, and then we evaluate them. The integrals with differential equations. So that will be the main meat, let's say, for today. That's what we will mostly talk about for the rest of the lecture. And so let's denote our basis by a vector, okay? And since these integrals are divergent, might be IR or UV divergence, they also depend, okay, we said they depend on D, or equivalently, they depend on epsilon, the departure from the integer dimension. And suppose that we have a vector of all uh, the master integrals. And in our case, for the bubble, we would have m equals 3. We would have these three integrals in this vector. And similarly, we have, so these are basis integrals, yes, basis or master integrals. And we also have x to be a multi-index. So it's x1 dot to xs, the kinematic variables. So in our previous example, for the bubble, these were, we saw p square, m1 square, m2 square. So 3, s would be 3 in this example, just to set up some more general notation. And then the fact that we have a basis means that if we differentiate these integrals, we can re-express them in terms of our basis. That's what basis means. So the fact that they are basis implies that, or maybe, that derivatives with respect to all the different variables also are expressed back into the basis. That's the asset that we have now that we have the basis. And this is an m by n matrix. And it's also convenient to package this into a total differential. So convenient just to have one piece rather than a set of equations. And so we can write this down, this set of differential equations as D acting on the vector I equals this matrix A, where this matrix A is really the matrix AX I times dxi. Just by multiplying every of these equations with D and summing over, you get, yes, this equation over here. And okay, you have some D's over here. So these are also one forms in the differential, yes, geometry language. So these are one forms. And how many are people familiar with one forms? Okay, everyone is familiar with one form, so this is nothing I should. If you want, they are yes, a convenient way to handle indices and deconstruct quantities that can be readily integrated. So if you haven't had the chance to encounter them, so okay, we have this now set of differential equations written in this way. And since they are a first order, it means that when supplemented, so if we know the value at a point, a single point with value I of x0 at point x0, computes, so solving them computes the integral. The fact that we have some variable, that the integrals depend on some variables, means that we can differentiate with respect to them. We get first order differential equation. All we need to compute our integrals is, okay, the value at one point, since they are first order equations, and okay, we need to be able to solve the differential equation. Sometimes this is hard, sometimes this is easy. Is it possible? In general, solving is very hard. Especially if we want, if we're keeping exact epsilon or equivalently D dependence. We generalized our integrals, we regulated them and so on by setting D general, but they come especially hard when you keep this dependence general. They become hypergeometric functions of very complicated type, for which even writing down series solutions can be very tricky. So that's life, it is what it is. But typically we are interested in indeed the epsilon expansions. It's typically in Lorentz series. In epsilon. Namely, we have that these integrals is a sum where every integral starts, okay, k e to the k. So yes, it doesn't start with epsilon to the 0. It can start with a negative power, 1 to the epsilon third. That means that the integral is divergent. And then you keep going. So to be more concrete, this I k0, epsilon to the k0 plus I k0 plus 1, epsilon to the k0 plus 1. So I'm not writing anything else here from the fact that the integrals have a Lorentz expansion in epsilon. They start at some power 1 over epsilon. Yes, some power can be positive or negative, and each of them might have a different power. That's why this is a vector over here. You could have some integral start at order epsilon to the cubed, another one at order 1 over epsilon, and so on. Given that we are interested in this expansion, and since the choice of basis is not unique, so choice of basis not unique, we can always redefine our basis, transform it. That's the idea. We can transform such that the differential equation becomes more easily solvable. And so let's imagine that we do a transformation where we take our basis I and we write it, yes, we multiply it with a matrix. Well, it could be the other way around. I guess I wrote it, well, let's write it the other way around, different from mine. So J is a new basis which depends on let me do it this way so that I don't screw up what comes afterwards. Let's assume that our basis is obtained from another basis by this transformation, okay? Or that the new basis is the inverse matrix acting on this basis. So it's a matter of matrix inversion, nothing too fancy there. And therefore, new basis obeys also, since it's a linear transformation. So this is Tj. The form doesn't change. The form of the equation. You multiply it with a matrix. What changes is how alpha, how A is related to, A prime is related to A. So Maybe this is not a surprise to you that this is a connection. This looks like a connection or like a gauge field in the language of physicists. So it also transforms as gauge fields do. So m to the minus 1. Okay, I drop now the x comma epsilon just so that I don't repeat all the time. So a dot m minus d m. Yes. So if it's a like dependent gauge transformation. If it was a global local gauge transformation, it was a local transformation it would like this. Since it's a global sorry, if it was global, it will look like this. Since the matrix itself is not yes constant, it has some functional dependence. It also picks up an additional term. So, anyways, that's how you can also convince yourself that this is the transformation, that this is how a linear transformation of the basis works on this connection, acts on this connection. So, let me write down a few more equations and then we take a break, okay? So by manipulating such transformations or by trying different things, we can hopefully choose this transformation matrix such that the new matrix appearing in the differential equations has an overall factor. Sorry, this is alpha prime, and this alpha tilde x. So indeed, very good. So epsilon can appear in principle everywhere in our original matrix A. But if you are able to find a transformation so that epsilon factorizes in front, and then there is a matrix that is completely independent of epsilon. So this is, let's call this so these equations are the so-called canonical or epsilon factorized differential equations. And they were proposed by Johannes Hehn in 2013. And in the remaining part of the lecture, so the remaining hour or so, I will show you how if one manages to arrive at this factorized form where epsilon sits in front, then this drastically simplifies the analytic evaluation of the Feynman integrals. So that's coming up. Any questions? Just so that I make sure I have enough time to tell you what I had planned and hoped for. So we basically were in the process of writing down differential equations for the master integrals. We got into a basis of all the integrals that contribute to a process, and we said maybe we can find the transformation from our basis I to basis J, such that, okay, the differential equation doesn't change in general form, but now the matrix involved, this alpha prime, has this epsilon factorized. And then I will now move on in the last hour to describe what the general solution of these equations are and how polylogarithmic functions come into play. So formal solution to these equations is constructed as follows. So we denote a path, gamma, parameterized by a parameter that goes from t0 up to t, with the endpoint being x0, the left endpoint, the starting endpoint, and then the right endpoint to be x. So let's also draw this. Okay. And then the general solution is, I will write something down and then really unpack it, because it is slightly, perhaps, yeah, not so often encountered. Others might have encountered this notation before, so it won't be that surprising, but I will make an effort to unpack everything that you see here. So what do we have here? We have some formula which has some kind of constant. So these are the boundary conditions. The values of the this vector, this basis of integrals at the starting point of the contour. And then we have the path-ordered exponential. So this is the path-ordered exponential. So which, okay, it has appeared, of course, in quantum field theory, describing Wilson loops and so on, of whatever comes on the right hand side of the equation, which is an integral of this one form. So it's an integral of a one form along this path gamma. Now let's make this more concrete. And already by looking at it, you kind of see roughly, but we will make it more concrete, that, okay, if you differentiate this, you bring this down because it's an exponential. If we think that one endpoint is fixed and the other one can move, this gives you really not just the exponent, it gives you at position x. So that's what this formula is telling us. But let's make it more concrete. And perhaps this is unnecessary and you understand this well already, but let's be pedestrian. So we already said that our alpha tilde is some, let's recall where this alpha tilde comes from. Some a xk times dxk. So these were the matrices of the differential equations with respect to the variables, and we multiplied also with some differential. So then we can also write this down. Okay, this is a matrix. Let's decompose it into a constant matrix part, and then something that has dependence on your variables x and so on. So let's write it down as integral over j and k, and let me use some colors also to like distinguish things. So this is some a j, and then you have some function, okay, x, sorry, h, j of k that depends on x, dxk. So I just, as I said, decomposed this matrix that also has dependence on x and, okay, some matrix structure into some constant matrix. And these are functions of x. So I I remove all functional dependence. And then we can also write this down as J alpha J dot omega J, where these are again one forms as before. Now, I really just took out these are scalar, so to say, yes, valued one forms. All the matrix content is here. You want to see an example of such a decomposition, or it is, let's see an example. Okay, just to be very, very concrete, for let's say that a x of k for some k equals, I don't know, 1 over xk, 1 over 1 minus x to the k plus 1 minus 1 over minus 1 and 1 is 1 minus x to the k plus 1 over x to the k. Let's say we have a 2 by 2 matrix, we have two integrals and so on. So, and then we can write this as 1 0 0 1 1 over xk, and then plus 0 1 minus 1 times 1 over x, sorry, 1 minus x to the k plus 1. So this would be, and let me make this purple, sorry, orange. So this is the constant matrices. And these are the h's. This would be the hk, or yes, sorry, hk, and then for different values of what is it? Yes, I guess this matrix. One. Yes, exactly. In this example, you would have two matrices, A1 and A2, and each of them would have an H1k being this thing and H2k being this thing. Okay? So this would be H1k, I don't know, H2k. Okay, that's all. That's this kind of decomposition. Nothing fancy here. Is it clear? Cool. All right. So then we can write this like one form over this path, integrate over this path as the same thing. Aj omega j, and integrating over this path means really taking the parameterization of the path from t0 to t, and then our like matrix valued 1 form A tilde. We wrote it like this. If we are taking a path, it's really parameterizing all the x's. And if we are parameterizing all the x's, this is what the integral will look like. So it's really a one-dimensional integral. And We can also call this Fj of T1. And this is also sometimes called the pullback. It doesn't matter if you, it's the pullback of this omega j along this path gamma. So called gamma star omega j. You have this form and you pull it back on this path gamma. In any case, it doesn't matter. It's very explicit what we do. And then, since we have reduced everything into a one-dimensional integral, then path order exponential is simply like the usual time order exponential that we have encountered even earlier, let's say in quantum mechanics courses. So then path order exponential is really time order exponential, time ordered exponential with respect to the variable t1 that we have there. And we can write down, let's see where, I should probably erase this side. So we have, therefore, explicitly path order exponential, the integral of this matrix valued on one form around gamma to be the path order exponential of epsilon. I'm just writing down that bit over here again. Epsilon, where was I? Yes, from t0 to t, jfj, t1, dt1, which is really, yes, this non-commutative, yes, version of the exponential, where you put, yes, things in a particular order. So this is, and it's the expansion. You write an infinite expansion. This is the unit matrix. This thing is a matrix because it involves matrices. And that's why it's non-commutative. And then you have, okay, the first order piece, there's nothing to order. So this is really what we just wrote in the exponent. Fj t1 dt1. And then we move on to write down the second order piece. Epsilon. This is where ordering matters. So t0 t dt1, and then t0 t1 dt2, and then you have some over j1, let's call them j1 a, j1 f, j1 t1, and then there's sum over j2 a, j2 f of j2 t2. So this is the, hopefully you have encountered time ordering in yes, quantum mechanics or quantum theory before. Since this is a matrix, you always write products such that the left factor is always at a later time compared to the right factor, factors on the right. So nothing mysterious either. And you keep going, of course, plus order epsilon cubed, and so on. And let's make some observations. So the first thing is that from this epsilon factorized form of the differential equations, you immediately obtain the epsilon expansion of the integral basis. So what you were looking for, yes, it's a convenient form of the equations that allows you to build your answers little by little in epsilon, and usually, I forgot to mention this before, you usually, when you have this epsilon expansion, you truncate it to some order. You don't care about the full expansion. You truncate it to whatever order is dictated by, yes, the loop order of your diagram and so on. It's you don't have to keep the infinite series. That's the important part. And then the second important piece of information is that the solution is an iterated integral, is in the class of iterated integral. Solution, epsilon, yes, epsilon coefficient. So expansion coefficients, let me write it, expansion coefficients are so-called chain iterated integrals. Again, mathematicians were there before physicists. Iterated integral. And let's define this. Well, it essentially copies the form that we have. It wasn't like this. Iterated integrals were invented before these kinds of transformations of differential equations, but we define this is just on the left-hand side the definition of an iterated integral, where these are some one forms. So these are, as previously, some one forms. And this is really just so happens to conveniently coincide with what we had in our expansion. F1, T1, T2, T0, T1, 2, T2, dot, 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 T0, Tr minus 1, Fr, Tr. Where the Fs are, again, related to the pullback of the function along the path gamma. So the same definitions apply as before. Gamma goes from T0. Shall I write it down again, or is it clear that? Yes, of these one forms. Shall I write it just to have it? Whereas before, or gamma goes from T0 to T, and F J of T is and well, since I use this definition, I think I can steal it, and F to R, exactly, F J T dt, okay, is the pullback gamma star omega J on this path, based on what I previously, so this is the same Fj that also appears here. So hopefully nothing is mysterious, and you see clearly that therefore these expansion coefficients, epsilon expansion coefficients, naturally fall within this class of functions that were defined decades ago by Chen, these iterated integrals. Okay, maybe that's an identification or pattern matching that yes, Yang was also mentioning before the start of the break. So how does it help us? Maybe we have identified that there's some particular class of function that shows up. How does it help us? Before we answer this, let's again give a concrete example of canonical differential equations and the transformation, in fact, to go to them. In the case of the bubble, our favorite example, I keep coming back to it to help make things concrete rather than abstract. So let's go back and now use the bubble to get canonical Ds. Again, bubble. All right. So you recall earlier today I said that I is, okay, I changed the order, but our basis was the two tadpoles and our usual bubble. And then this is for you. That J defined as just a rescaling of some of these integrals. I. Is that mine? Oh, goodness. Forgive me about this. So this is a transformation, and I need to tell you what lambda is. Lambda is lambda of p squared m1 squared m2 squared equals p squared minus m1 plus m2 squared 2 minus m1 minus m2 squared. The so-called Kellen function. Let's see how observant you are. Do you recognize these pieces at all? Did we run into them before? Do they look like something familiar? Okay, yes, what? Very good. Very good. Excellent. Excellent. So what Sasha said was that when this is zero, when this is zero, these are the Landau singularities of the graph that we determined last lecture, and this is not an accident. Okay. But okay, I'm going with this small aside. And so this transformation, these were our initial integrals. This is a rescaling of one of them. And then this transformation makes the differential equation canonical for J, canonical in D equals 2 minus epsilon, 2 minus 2 epsilon. So to get an epsilon factorized form, okay, this will turn into epsilon when we set D to be near 2 dimensions. This might look funny, but as I mentioned, we can always relate integrals with loop integration 2 to 4 and so on, so this is not a problem. We can also, from this, then obtain the 4-dimensional integral that interests us. And so, in particular, we can write down what the differential equation is. So dj equals epsilon, and then we have d log 1 over m1 squared, 0, 0, 0, d log 1 over m2 squared, 0, and then some d logs, let's call them w minus, d log w plus, and then here in the corner we have p squared divided by lambda. I won't write lambda off, but it's this lambda, okay? It's this lambda over here. And also, to be completely concrete, these pluses and minuses refer to minus m1 square plus m2 square minus plus p square minus square root lambda, again this lambda, and then we have the same thing in the denominator almost, minus plus p squared, but with an opposite sign, plus square root of lambda. So this is very concretely, in the example of the unequal mass bubble, how the differential equations look like. Okay, this, sorry, I wrote what alpha is, so times j. And epsilon only appears in front. There is no dependence of epsilon over here. So that's, of course, the first observation, as we would want if this is a canonical form, sorry, canonical differential equation, yes. And then, do we notice something, let's say, more specialized, more, yes. Is this the most general form of a differential equation? Do you notice something? Yes. Well, what is the form of, how do the one forms look in this example? We also call them sometimes letters appearing. So, okay, in this form, in this differential equation, you have the constant matrix. So there is a constant matrix that comes multiplying this bit and this bit and this bit and this bit. And these are the forms that appear in the differential equation, right? This matrix alpha tilde, sorry. So this 3 by 3 matrix is our alpha tilde, and has a constant matrix part and then some form part. Well, you see the form because there's the D over here. There is no D. There should be. Sorry. That's a D log. Very good. Thank you. D log. That's very good. Thank you. D log p squared over lambda. Exactly. It's a matrix of log form, D log forms, logarithmic forms. Are logarithmic. Are namely, exactly. D log of some function f. And this is often occurring. So this is the often occurring in physics, in really calculations, in many calculations, and also the best understood case. Best understood case. So it's a special case of iterated integrals, and it's related, very closely related to special class of iterated integrals known as multiple polylogarithms. Or MPLs for short. And let's define those. So these are defined as G with argument Z1 to ZR, Y, and it's from 0 to Y, dt1, t1 minus C1, 0 to T1, dt1 over T2 minus Z2, dot, 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 ttr over tr minus zr. With special case also, with special case G of 0 r times Y to be 1 over r factorial log to the r y. Is it clear that this is a special class of iterated integrals? I mean, that yes, they are described, yes, they are specializations, special cases. Shall I elaborate on this or shall I move on? I can elaborate, okay. So first of all, you see that there is this ordering. Okay, this I did not write. So this should be from 0 to tr. This is tr minus 1. So first of all, there is this time ordering in this time kind of definition. Every innermost integral, yes, the endpoint is the next variable of integration. Yes, so exactly. TR is smaller than TR minus 1. Exactly. And so, okay, if I will put it in the notes, but you can show that they fall in the class of iterated integrals by letting, okay, I will just write it down and then so that we do say a few more things. So let me can show, okay, can show by letting W Zj to be dx over x minus zj. So these will be our forms that depend on this. Well, they have this parameter zj, which is treated as fixed. You can think of as a number, at least for the time being, 2 or 3, and then and choosing a path gamma that goes from 0 to t with gamma 0 equals 0 and gamma t equals y. And then this definition over here is really just w z1 for the dot w zr. And one can show, for example, by choose simplest path parameterization where t equals x. So okay, we have a we are think of these forms as having one parameter x, and we can okay, it's a one-dimensional space, a path. We can choose the path, the parameter, the variable t parameterizing the path to be equal to x, and therefore you can maybe also work it out a little bit that this definition precisely boils down to this. And also, so this special class, okay, they also, so R is called the weight of the multiple polylogarithms. And this class definitely contains classical polylogs and also other cases of polylogarithms that were previously introduced by physicists. So I will let me also write this down. So MPLs contain classical polylogs. And again, it's not hard to see from the definition, but we can just to get some feel of them, see that G of 0 r minus 1 times, comma 1, y coincides with the definition of the weight r classical polylogarithm. And they also obey many identities. I will not have time to even list the main classes, but let me mention one very prominent case. This is the so-called shuffle algebra, which tells you that a product of two MPLs can be written as a linear combination thereof. Z1 ZR, G ZR plus 1 to Z, sorry, comma, with, yes, Y as rightmost variable, and then G ZR to Z, sorry, let's make this R1, R1 plus R2, Y. So they have to have the rightmost variable as the same, but this we can write as a sum of G functions of MPLs that now have a vector that is size n1 plus n2. So I was really looking for me. Okay, where these are shuffle permutations. And shuffle means that those permutations those that preserve the relative ordering of Z1 to ZR1 and ZR1 R1 plus 1 up to ZR1 plus R2. And when I mean relative ordering, I mean really like taking two decks of cards and shuffling them. You take them and you make sure that cards from one deck are mixed with cards on the other deck, but the relative order of each of the cards in each of the decks remains the same. That's what shuffle algebra means. And in light of time, I will not present an example, but well, we can discuss it offline if people are interested. In 10 minutes. Okay, we have 10 minutes. All right, maybe very quickly. Very quickly. Okay, there's a simple example that one can write down. Okay, so let's say Z1, Z2, Y, G, Z3, Y. Who will tell me what this is? Sorry. Just a typo. Thanks for pointing it out. Where these are, yes, permutations sigma. So shuffle permutation sigma. So if sigmas are all permutations, a subset of them are the shuffle permutations. And so let's see it also in practice here. Who will tell me what the right-hand side of this is? Yes. Tell me. Precisely. So, okay, here we just have one element. You cannot mix any order. But here you have Z1 and Z2, and you see that in all of those, Z1 always comes before Z2. And this is also very easy to prove. It really has to do with the fact that you split. If you have a product of two integrals, you are integrating over a square, and then you have to split the square into triangles in order to be able to have a particular order for the integrations, and this gives you this kind of shuffle algebra, which is not tied to G functions. In fact, it holds for any iterated integral. And yes, there are other interesting identities that I will have to skip, but the interesting thing about these functions, and this is, I guess, why they have been so really many, yes, incredible progress has been achieved in calculations of scattering amplitudes and Feynman integrals because physicists understood these functions, which were also, I should say, also go by the name of Goncharoff polylogarithms. So they have appeared again independently in the mathematics literature, and it was understanding this and decoding these properties that really led to I would dare say, a revolution in yes, perturbative quantum field theory calculations. So I will just say a few words for those that are interested to look at that further, or MPL, and maybe give the basic idea. All MPL identities may be eliminated namely in favor of the basis. So write two seemingly different expressions as the same. With the help of the coaction, the so-called coaction, or coproduct, sometimes called coaction or coproduct. On MPLs. And I will only be able to give the essential idea. This will not cover, unfortunately, this set of lecture series. And okay, coproducts appear, or Hopf algebras, related Hopf algebras appear also in other areas of physics and mathematics, integrable systems, and so on. In essence, this coaction coproduct reduces proving, let's say, f of r of x equals, let's suppose you have some identity. Okay, you want to prove this, and these are, let's say, these are weight r expressions of MPLs. So you're trying to figure out if they are equal to each other. And the idea that the coproduct does very efficiently is to prove instead that the derivative of the function r of x equals the derivative of the function f prime, and also that f at a point x0 equals also the function f tilde at point x0. So this is value at a point x0, and these are the derivatives. But the coproduct or coaction can do it in a very efficient and systematic manner. So with this, you can, for example, drastically simplify your calculation because you have a basis, you have the minimum number of functions that you then have more compact expressions. For these functions also, very efficient numerical evaluation programs have been written down, and this is helpful for experiment. These are being used by phenomenologists. So this was more or less the content of the course, but let me finish with a short epilogue, just to summarize some of the lessons we taught. But maybe, yes, if you have questions about MPLs, I propose you save them and then we have a discussion in the end. So let's give an epilogue of the course. So we saw especially today that canonical differential equations, or I hope I convince you, are the current state of the art for Feynman integral evaluation. What I did not tell you, but this is a good point to say, is that yet finding the transformation that takes you from a usual to a non-canonical is hard. It's quite hard. If you are able to find it, then you can do great progress, and with this respect can simplify significantly finding this canonical transformation if the letters that I defined, or these forms, if letters, this Wi, which are in particular logarithmic, so logarithmic forms, are known beforehand. And this goes back then to connect to the Landau equations, which might have been mysteriously disconnected to what we discussed so far. If we going back to a bubble example, we notice that these functions appearing in the logarithmic forms are okay. I will put this in parentheses, but they are essentially m1 squared, m2 squared, p2 squared, and then this lambda, or maybe let me write it explicitly, p squared minus m1 plus minus m2 squared. And these are nothing but the solutions of the Landau equations. And so in recent work, we showed that this relation holds quite generally. And that's how, as I promised to you, the Landau equations can help us actually evaluate the integrals. And this is work I did with Christoph Tlapa, again Martin Helmer. Yes, and also my student Felix. I was wondering about the order, and I think this is correct. Yes, good. So we can use it. It wasn't an accident that the solutions of the Landau equations appeared in these letters. And we yes, analyze this and show that it holds quite generally for polylogarithmic Feynman integrals. And so just to if there's one punchline to remember from these lectures, is that the knowledge of analytic structures uh, significantly aids evaluation, the actual evaluation of scattering amplitudes. That's what we saw in the BCFW. Construction of three-level amplitudes and Feynman integrals, which is what we saw, yes, at loop level. Analytic structure as captured at loop level by the Landau equations. And this, you also noticed, definitely bring this field with very close interplay with mathematics. I mentioned, yes, many areas of mathematics, algebraic geometry, number theory, topology, that come into play. And it's a very fruitful dialogue between physicists and mathematicians. Thank you very much for your attention. It is delayed? Okay, so that means that we can discuss questions.
What do you mean by analytic structure? Do you mean like the entirety of how?
So in the very first instance, analytic structure means where does your function have singularities and what type of singularities they are. So that's the very first question that analytic. So poles at tree level and logarithmic singularities at loop level.
Not for example, sort of sunset arguments, and you put it in that taxonomic order, you ended up with an expansion D is 2 minus first. Then if we wanted to be four-dimensional, then that epsilon we need to take first to minus 1. And then your epsilon series is going to converge very slowly.
What you can do is that you can relate two-dimensional integrals to four-dimensional integrals. Or put differently, if you have a basis of integrals in 2 dimensions, you can generate the whole new basis of the same integrals but in 4 dimensions. You can increase the dimension by 2, and this is related to the work of Tarasov that I mentioned earlier on. It can be used to reduce tensor integrals to like scalar integrals, but more generally, it allows you to shift the dimension of loop integration of integrals. So this is also taken care of. You can always go back and find what your four-dimensional integrals are.
That's another approach from what I heard is that you have those tensor indices, Lorentz indices. You can trade them for Lipper group indices and then work the Lipper group. And the big point is fixed by a Lipper group, then you can construct everything in the same way. LonTI too? Or I'm not sure.
So what you are describing seems to be what we discussed about BCFW, but because little group is helicity for the Lorentz group. So what you seem to be describing is essentially, okay, the spinor helicity formalism and the fact that you look for amplitudes with well-defined helicity, since it's a quantum number that you like, that is a good quantum number for massless particles, you can group your amplitudes according to helicity. But then It depends. So if you are asking, can you use it to evaluate Feynman integrals for a generic process in QCD or in a generic gauge theory? The answer is that no, this is hard. This is hard. One of the difficulties is that spinor helicity is strictly defined in integer dimensions, in 4 dimensions, in 4 dimensions, because that's when the Lorentz group has this very special factorized structure. But if you want to regulate Feynman integrals, you have to go away from 4 dimensions, and then it's yes, it's not very efficient. It's not. What one can do is, yes, generalized unitarity. Look for cuts of of integrals. So if you try to localize, so if you replace your propagators with delta functions, you kill many integrations, and you might end up with a quantity that has no loop integrations left. This you can, so this will be in the end uh, 4 dimensional. This will be free from divergences, and this you can use also spinor helicity or such inspired methods.
Does it make any sense to look, or rather, any of this method work for Wikipedia?
Yes, I don't see any showstopper. In fact, if you are yes, if you weak rotate your QFT, you are in Euclidean signature, then you have more power, and you can show that, for example, yes, Feynman integrals. Oh, very good. The pizza is here. In the Euclidean region are always free from singularities, for example. And so it's always at the boundary of the Euclidean region where singularities show up. So indeed, with this yes, you start with something that you know well when you are in the Euclidean. Exactly, uh, everything is positive definite. The denominator of the Feynman integrals never vanishes, and so you are safe. And it's a good starting point to then analytically continue to, yes, Minkowskian kinematics. Thanks a lot again. It was very enjoyable.